Good morning, everyone. My name's Ali King, and I'm a data engineer at FanDuel, based in Edinburgh, Scotland. I came to Amsterdam last year for this conference and enjoyed it so much that I returned here as a speaker. So today I'm going to be talking a bit about data pipeline evolution. I'll be covering some of the challenges of building a reliable data pipeline system and then iterating on the initial design to make it faster, more efficient, and better adapted to the needs of its users. I'll also be briefly covering some of the technologies used, but overall this is a high-level talk suitable for people not overly familiar with big data technologies. It's based on the experience of FanDuel, a high-growth, data-driven company. We'll also be looking at building a data engineering team. So, who am I? I was the first new hire to the FanDuel data engineering team, joining in May 2015. This was my first time working with big data technologies and also my first job coding in Python. So I'm sure you can imagine that 2 years ago I hit one hell of a learning curve. My previous career path was a little unorthodox. I started working as a programmer after the age of 30, so I guess you might call me a late developer. You don't have to laugh, it's okay. Over the last few years, I've gone from learning to code in evening classes to doing contract work in business intelligence. I then did a remote internship in open source software, working on semantic data. Did that with Outreachy, which is a scheme that I very much recommend to get people from underrepresented groups working in open source. And also worked in startup companies, along with teaching people to code and giving talks in my spare time. Throughout this time, the key focus of my learning and development has always been around data. And actually, this is my last week working at FanDuel. On Monday, I'm going to be joining a healthcare analytics startup called Spiritus Partners, also based in Edinburgh, and combining my big data expertise with blockchain. Who knows, I might be giving a talk about that in a year's time. I live and work in Edinburgh, the capital of Scotland. Edinburgh has a thriving tech scene with successful startups scaling up to high-growth companies. There's also a large financial services sector and offices of multinational technology companies like Amazon, attracted there by the highly skilled technology workforce coming from the universities and other paths of learning. It also helps that the cost of living isn't too high, although the weather could be better, of course. The company I work for, FanDuel, is a big player in the world of daily fantasy sports. Fantasy football is a popular hobby in the UK, US, and many other countries. Sports fans pick their ideal lineup of players and see how they do against their friends over the football season, based on the combined points of their players for goals, saves, and passes in real-life games. Daily fantasy sports works the same way, but over a shorter time frame. Pick a team out of the players who are playing in Saturday's matches, say, and then find out the same day how well you've done. The company was founded in Scotland, but its biggest market is in the United States, covering American football, basketball, and other sports popular there, though you can now also play in the UK as well. So what made FanDuel decide to invest in building big data infrastructure? Fairly obviously, we had a lot of data to start with. FanDuel has millions of users and many more times as many games, lineups, etc. And that's just the data from our own databases. There's a lot more information such as web analytics, marketing communications, A/B testing, push notifications, data from payment providers. And by bringing all of that together, we can understand more about how to make our customers happy and succeed as a business. I'd characterize FanDuel as a medium-sized company as far as data goes. You've got your Amazons and Facebooks with tens of thousands of staff, massive dedicated data centers, and having to invent new big data technologies from scratch. And then you've got smaller startups where the entire staff fit in a room. So FanDuel fits somewhere between those. We've got a few hundred staff, of which about 100 engineers, most of whom are based in Scotland. And hopefully some of what I can tell you about developing data infrastructure as the company grows will be useful if you're on the same sort of journey. I was inspired to write this talk as it became apparent that many people don't know much about what a big data engineer does. Even of the software engineers, it was a bit of a mystery what our team did. A common assumption is that I'm a data scientist, and although there is some overlap in the skill sets, it's not quite the same thing. The role of the data scientist is to experiment and discover new patterns and relationships which can be used to make decisions on running the organization. My job as a data engineer is not so much about making discoveries, but building a system which delivers data in a consistent, reliable, and timely fashion. It can then be used by data analysts, data scientists, and people in other roles across the business, like providing statistics for top management to make kind of big decisions, to make decisions about the business direction. We can automate a lot of analytical and data science tasks so that others can spend less time on tedious processes like cleaning and preparing data, and more time using the skills they're being hired for. In this, some knowledge of data science is useful, for example, if you want to productionize a data science model. But it's more about producing quality code which moves and transforms data to where it should be. When explaining my job to other people, I sometimes describe it as plumbing, making sure data flows from one place to another. When working with open source big data technologies, the main languages supported for working with the main frameworks, libraries, and APIs and whatever are Java and Python. Languages which run on the JVM, like Scala and Clojure, are supported too, but to a lesser extent. You'd probably have to do a lot of like Java interop if you're using those languages. Which one a company chooses is often down to the general technology choices within the company and availability of engineers, as well as support for the languages by the specific technologies you want to use. Python, to me, makes a lot of sense because, as well as being more concise and easier to work with than Java, it also allows for working more closely with people on the data science side, as Python is one of the languages most widely used in data science. You could also argue that Java is better as it's statically typed, so better for avoiding mistakes where data is converted into something it shouldn't be. But hey, I'm not here to argue about programming languages because we could be here all day on that. FanDuel is a startup company which has grown rapidly from its foundation in 2009. In an early stage company, if someone needs to get some figures, they can simply run a query on a replica of, we hope, the production database. Very simple queries can still be run up to relatively large table sizes, but anything involving joins and more complex operations tends not to scale well up to millions and billions of rows. In addition, the databases used by an application are optimized for transactions so that individual actions can update or return data. Making a database perform well for the purposes of analytics requires a different setup entirely. So the first step is to get the most useful data into a data warehouse of some sort, optimized for analytics, and updated on a regular schedule. Often the most immediate option, particularly for a fast-growing company with a lot going on, is to get an off-the-shelf data warehousing solution. So that's what we did initially at FanDuel, and it worked well for a while. The data was imported on a schedule, the analyst analyzed, and the data drove the direction of the business. Now, that would have been fine to continue if not for the fact that the size of the data was growing at a massive, exponential rate. So the positives of using a software product for data warehousing are that it can be managed by relatively few people. It's been built and tested by the software company and works for other users besides yourselves. The negatives include that you may have less overall control over your data. Data security and legal compliance can be a bit trickier, and it's harder to make changes. And the time to respond to your bug reports and feature requests is beyond your control. It's basically down to the company's service level agreement, which might not be quite to your liking. The biggest one is probably pricing. Once you get to a certain size of data storage, it starts to become pretty expensive, and you'd be better off hiring a few software engineers to take care of it for you in-house. So the decision was made that we needed our own in-house solution for processing and warehousing our data. At this time, the data team did not yet exist. Several of the company's Python developers were brought in to start building a pipeline to replace the previous system. By this time, a fair amount of the company's infrastructure was on Amazon Web Services, so it made sense to use their Elastic MapReduce clusters and Redshift distributed database to process, transform, and store data from the company's production databases. Other cloud providers are available, of course, but AWS is what I'm most familiar with, so that's what I'm going to be talking about today. But I think you can get equivalent services from Google and Microsoft and whoever. So the whole process imported key tables in full each day and took several hours. If this sounds familiar, that's because the process is basically a distributed version of extract, transform, load, ETL. Instead of having a single process extracting data from a database or other source, multiple nodes of the elastic MapReduce cluster each import slices of the tables. The transformation phase involves some shuffling data back and forth between nodes because sometimes you need to combine data which hasn't been imported onto the same machine. Finally, the data is imported into Redshift. In this case, we're completely replacing the data from when it was last imported yesterday. Here are the technologies we're using at this point. The source databases are MySQL, and we're using the open source Scoop tool to import this data onto the elastic MapReduce cluster, which runs Hadoop. Data transformations are handled in Hive, which uses SQL for describing tables, and then the derived Hive tables are imported into Redshift. Much of this is managed using Luigi, a task management library originally developed by Spotify, which has classes for working with all these technologies. These can then be modified as needed using Python for any custom functionality. Redshift is Amazon's distributed data warehouse product. It can be queried using PostgreSQL, or a subset of that language anyway. However, it has a few properties different to traditional relational databases. Firstly, you cannot enforce a primary key. It seems kind of basic for a database, but it's not feasible to check across what could be a large number of machines whether a value already exists. And it doesn't have indexes, which you would normally use to allow a quick lookup of values for joining and sorting. Instead, it has distribution keys and sort keys, which do a similar job. These affect how the data is stored across nodes. So by choosing these wisely, you can limit the amount of data which needs to be sent between different nodes in order to carry out a SQL query. Redshift is proprietary. I did look to see if there was an open source alternative to recommend, but it turns out that due to the way that the hardware and the software are coupled in Redshift, other distributed databases aren't really comparable in performance, at least as far as I'm aware. The advantages of the full import approach are that you have a single process, so you can tell users when the load is done, and that's it. It's relatively simple to understand and debug, and performance and completion time won't be affected by other import processes on the cluster. However, the downside is that it's slow and in some places inefficient. For example, if most rows in a table are infrequently updated, or once a row is added, it's never updated, so it's an append-only table, you're reloading a lot of the data each day that's exactly the same as yesterday. You could try scheduling the load to run more frequently than once a day, but it takes a similar amount of time for the new load to happen, and the less important and less frequently updated tables are updated along with the more crucial ones. So, how to solve this? The next stage of evolution is to incrementalize some parts of the load. There may be some parts where it's unavoidable to re-import the whole table every time, but there are other areas where this can be improved on. There will be some data which there is a lot of demand from users to get the latest figures. With FanDuel, an example of this is games and entries. We need to know the details of games that have just completed and also what entries are live at the moment. Once games are marked as completed on the system and all the scores are worked out, we can import just these games as the data isn't going to change anymore after that point. And this data, we want that to get that data as soon as possible to find out, how much money we've made, basically. So once they're completed, we can import them, as the data is not going to change anymore. And similarly, if a table like payment transactions, say, has a unique ID field which is auto-incremented, so it just kind of increases, and you can just mark, well, what was the last value that we imported, and then start again from there. Another option is to import all rows fitting certain criteria on a regular schedule. For example, you might want to import all games which are currently open and that have players but not finished yet. So basically the ones that are live just now, and just import that on a regular repeating schedule. This allows some of the most critical tables to be updated at a frequency suitable to their use, and more slowly changing data to continue being updated in full daily. So we've basically got, we've got the full import, and then we've got some incremental imports for things that we can import more frequently. At this stage, we started to use Apache Spark for some of our import processes, both full import and incremental. Spark is an open source, fast, in-memory data processing engine, which allows you to perform more complex transformations on data than you'd be able to do efficiently in SQL. It also has a bunch of libraries, including ones for machine learning and data science algorithms, allowing you to incorporate things like prediction models into the regular data import processes. The advantages of bringing in data by the batch are that it allows you to update more rapidly changing parts of the data set more frequently, allowing users to get more up-to-date reports. This is limited by the design of the data sources you're importing from. So if a row in a table can be updated after first being written, it may be hard to work out whether it has changed from the previous import. You basically need to do a comparison between the two. Also, if there are multiple import processes instead of just the one, it's a little harder to keep track on what's happening and how fresh different parts of the data warehouse are. The web of dependencies of the tasks can be a little harder to navigate, although using a task management library like Luigi will help with this. When you're piping your organization's own data, as opposed to that from external providers, there's a great opportunity to streamline the process by working together with the engineers who develop the source databases. If the table design is such that you can identify which rows are new using a simple SQL query, a lot of duplication can be eliminated. So you can say to the application developers, how can you help us not have to import the whole table each time? And they can do things like make some tables append only with an auto-incrementing ID, so that the rows aren't going to change after they're written. You can then check what the maximum ID was you imported last time and carry on from there. Or for tables where the data does change, like say a user details table, add a column for last updated time and only import rows which have changed. There's also the possibility that other engineers can provide an API to send the data to the system instead of directly importing it from the database. You may not have the same capacity for collaboration with external data providers, but could always put in a feature request and maybe use the leverage you have as a customer to try and get it implemented. So what next? With the incremental import model, you could continue to increase the frequency and reduce the batch size so that there are many more tasks running throughout the day. But this produces diminishing returns. After a point, the overhead of the running of the process and storage of task metadata becomes a bit much. So what if you can move to a more event-driven model where the import process effectively starts when something happens and doesn't have to wait? Amazon Kinesis acts as a queue where you can add items on and store them for a specific time during which they can be read and archived or used for some other purpose. Apache Kafka is an open source alternative which does similar things. So you can write an event collector which, when something happens in your application or API, pushes an event onto the queue. Events might be something like a customer logging in or making a purchase. So you can read events off in regular batches, and you've got a fairly up-to-date record of what's happening in terms of events for the database. Where the possibilities get more exciting is you can have multiple consumers reading events off of this queue independently and have them pass the data through a data science model and generate responses in near real time. Some applications for this are fraud detection, personalized recommendations and content, and up-to-date dashboards of activity which use predictive models. Using data streams like this can massively improve data latency and give you a feed which can be used for near real-time responses to patterns in activity. However, the architecture for this is different to the full and batch import processes and does not of itself integrate well with them. But by archiving the data and making it available alongside the more conventional imports, behavior can be joined up to other information about the user to give a rich profile for use in machine learning models. So basically what we've built at this point is almost Lambda architecture. You have one layer of batch processing going on, and there's a separate event stream on top of that. However, as we're not doing much with the events other than archiving them in batches at this point, it's not quite true Lambda. This means that the different parts of the data have different latencies. So in this hybrid model, you might have conflicts between the different sources in terms of truth. If the users are educated about this, they can use the correct data source for the purpose and understand maybe one thing like supersedes another. It may be extremely important to the business to know what's happening right now for certain key events, but through the occasional lost and repeated data in the stream, you wouldn't necessarily use that for auditing. So you would probably want to run that through the batch process and do copy checking to make sure that there's no duplication or sort of faults in the data. The main challenge of building and maintaining a distributed data pipeline is scale. Given the amount of data you're importing isn't going to go down, the trick is to keep things running evenly while adding more layers of data import tasks. So you're requested to add more import processes, but as there are now more tasks running on the same number of nodes, it takes longer for the last of them to complete. That means that we need to work continuously on streamlining and improving processes in order to maintain performance in an increasingly complex system. With the exception of DevOps, the data engineering team is probably the team at FanDuel who work most closely with the nitty-gritty of system performance in the cloud. We can experiment with different parameters within tasks in order to get them to run more efficiently. For example, changing the number of mappers, memory allocation, or task prioritization. A tempting solution to dealing with performance issues is to add more nodes to the cluster. And I think certainly in the earlier days of FanDuel, it was a case of throw more machines on the fire. But however, it's not going to make you too popular with the finance departments because computing power is pretty expensive. One of the things we can do within data to solve this is to try out different hardware configurations for computing clusters and work out the trade-offs of cost and performance. Making estimates of how changing the computer hardware might affect cost and speed. So, for example, you might be able to increase the number of cores, change the type of memory, switch to a faster processor. Perhaps a larger number of cheaper instances will do the job. With a cloud computing provider and steady build and deploy systems, spinning up a new cluster and benchmarking performance is something that is quite straightforward to do, and then you can basically experiment a bit and then find out what's the best combination of cost and performance. But what if you could take some of the increasing number of processes off of the cluster? One improvement we're currently evaluating is incorporating some new cloud services into the pipeline, which could reduce maintenance requirements and, importantly, cost. Amazon Web Services has a new service called Glue, which is a simple interface for mapping and running data extracts and transformations, deducing the schema and notifying when this changes. And best of all, you're just charged for the running time of the process. It's a serverless process. And so you don't need to keep a cluster running the whole time. For cases where we're importing the contents of a table or file with minor changes to the structure of it, these processes could be moved off of the main MapReduce cluster, so we wouldn't need as many nodes. Similarly, Athena allows you to run queries on flat files in cloud storage using a syntax similar to SQL. So this could allow for storing more data in the cheaper cloud storage facility. In the case of Amazon, that's what's known as S3, rather than having persistent data on the cluster itself, which means you need to have nodes with more memory on them. Both of these are serverless services and were announced at Amazon's reInvent conference last year. If you're an existing AWS customer, you can sign up for the beta and experiment. I don't think they've gone full production at the moment, but it's something where you can have a go on that and benchmark that and check and see check how it goes against your existing processes. The most interesting technical book I've read recently is I Heart Logs by former LinkedIn engineer and co-inventor of Kafka, Jay Krebs. It's a short book, but it was a real game changer for me in terms of understanding new possibilities in designing data systems. Instead of having multiple data processes with different latencies, why not just record everything into a single, distributed, immutable log in near real time and use that as your single source of truth? Kappa architecture combines the batch and streaming layers into one so that the single stream processing layer handles the incoming data, and the resulting history log can be used by all systems, not just the warehouse. If you take one thing away from this talk, go read this book. You can actually get it for free just now, if, in exchange for giving your email address, from the website of Confluent, which is the author's new company. In many cases, particularly with fast-growing companies or ones blessed with much legacy infrastructure, large-scale data processing and storage is an afterthought. But what if you could start from the beginning? We all love a greenfield project, right? If I was to start architecting for a new data system, I think I would go towards the Kappa architecture, just basically making data the center of things to start with both the company's analytics services and other operational systems using a single distributed log for data sharing between them. Of course, most of the time we don't live in an ideal world. A common pattern is, with startup companies particularly, is to begin with a single monolithic code base. In our case, done in PHP, providing the changing functionality of their core products. This then begins to be broken down into microservices as the company scales. To start off with, big data capability might not be a priority. I mean, if you're going to have enough data to need big data? But as the services multiply, building in a common data infrastructure will save a world of pain in the future. Initially, FanDuel found it extremely hard to hire engineers with relevant experience. They put out ads looking for people who'd worked with Hadoop, Hive, Pig, Redshift, and at that point, there were very few programmers in the market with that background. If you think about it, relatively few organizations have both the size of data and the engineering investment to have a large distributed data infrastructure. So there weren't many engineers available who'd worked with big data before. In that situation, the best strategy is to hire people with transferable skills and experience fitting the role. This might be traditional SQL ETL developers with some experience of using open source frameworks and general purpose languages. Perhaps someone with functional programming experience because of the use of MapReduce. But overall, looking for a track record of mastering new technologies and constantly updating their knowledge. Any competent programmer with an interest in this area should be able to pick it up fairly quickly. The FanDuel data engineering team incorporates a good balance of strengths in each of these areas. Many computer science undergraduate degrees have a module also on big data and distributed systems, and there are an increasing number of master's level courses which specifically cover the subjects in more detail. Some of the data engineers I work with hold MSCs in operational research or data science. And this, combined with previous experience in computer science and programming, makes them very well suited for the role. I was pleased to see there's a new MSc from Dundee University in Scotland in data engineering. So having hands-on experience of working with all these sort of big data technologies and optimizing things. And I'm sure there will be other similar courses in future from other universities. As well as technical skills and qualifications, there are a few other key attributes needed. Given that an organization which is recruiting a data engineering team is likely to have at least several technical teams and be adding more developers all the time, communication skills are extremely important. I would rank this as a #1 predictor of success for software engineers generally. And since data often interacts with people at all levels across the company, being able to effectively communicate in a variety of contexts using different media is vital. Also, the technologies used in data engineering are improving at a pretty rapid rate. So being a self-motivated learner able to keep up with new developments is extremely important. And of course, a passion for data is important too. So today I've told you a little about the journey taken by a company with big data needs, building both the pipeline and the team to build and maintain it over the course of a few years. I hope this will be useful to people who are on or about to embark on their own journey. If you'd like to find out more about data engineering or FanDuel or anything else within reason, I'll be happy to chat later. Now I think we've got time for a few questions. Well, certainly, I think the difficulty is once you're, one of my colleagues actually gave a talk on AWS services called Learning to Love the Lock-in. And the thing is that once you're with one cloud provider, particularly if you start using services that are specific to them, like say in the case of Amazon, then AWS Lambda, then it does make it harder to migrate. So once you're in, so certainly, I think it's just that it would be very difficult for us to migrate at this point. But if there was enough of a business need to do it, then I guess that's something that we would look at.
How do you manage the schema of the data?
Sorry, how do you manage the schema?
Yeah.
What do you mean the schema for the end sort of data warehouse?
I mean the source of the data is changing often.
Source data, most of what we import is from internal systems, and so we're able to then so work quite well with the other teams. What we're talking about, like sort of collaboration. Then, if there's a schema change, then someone in a team working on that will give us advance notice, and we'll be able to look at their source code of what's happening there, and then make changes in accordance with that. But I think we are looking at potentially moving more, sort of towards having like a kind of a combined sort of data service, so that you have like data discoverability between the different microservices, say.
Are you still using Redshift as a final database?
For a lot of purposes, so basically that's very good for data warehousing and for doing queries on very large tables. That's basically what it's built for. But you can also extract data from there and say if you wanted to, sort of take data from there and then say export it and then run it through a Spark model or something like that. Then you can extract data from there, and that's what the people on the data science side do that. And I think some of the data analysts as well do take data out of there. But that's the kind of the main data store. It's kind of where all of the data is, and you can combine things with each other. But yeah, you can extract things, but if you want to do SQL queries on things, then that's probably the place to do it. All right.
The first step of your presentation.
Yeah.
But I'm struggling with the fact that, for example, there's not support arrays, and it's not sexual.
Yeah. Yeah, I mean, I know. I've worked with Postgres before this, and basically, as I say, Redshift uses a limited subset of Postgres. So maybe just don't think of it as being a Postgres database as such, but it is, a database that you can query with Postgres syntax. But yeah, there are some limited things, particularly with all the kind of more complex data structures that you can get within that. But again, if you need to do more complex things with things, then you can extract them and use them in another system. Yeah. Mm-hmm.
What about the data security, the data quality you got? Like you got several data sources, if I understand correctly.
Mm-hmm.
How dependent are you on them? Like if one fails or decides stop the delivery or whatever, does the system collapse then or whatever?
Well, basically, we're aware that if the data source fails, so we've had that occasionally with, say, external providers, but we know that because the import tasks have failed. So we get notification that that's failed. So, for example, we import data for some external data, like payment providers say. And I think there has been cases where they've changed something about the data format and not told us. But we know that because the job fails. We also have data quality checks on the import, and so we're aware of you're able to set sort of email notifications for if something goes wrong with that. But yeah, we usually know pretty fast if a task isn't running.
But are there any alternatives? Now you get your payment details from, for example, payment provider or any other data. What if your data provider would decide to stop delivering your data? Do you have any alternatives then?
Well, I guess if you're talking like, say, a payment provider, then then probably we'd see about moving to another payment provider because we need to know the transactions that are coming through.
For example, the game details, for example.
Yeah.
Some source or provider.
Oh, you mean like kind of say sports data? Yeah, I mean, actually, sports data at FanDuel is processed by it's like another team that deals with that because they basically pass they get these box files and then they pass those in sort of near real time and then they update the scores through the website there. But yeah, they do work closely with the sports data providers and ensure that things are coming through because you want to have like a kind of live score updates and see how you're doing. So that I guess that's a matter of working with the data providers. It's not just like reading it from some open API. It is like a paid for service essentially.
So if I'm coming to Amazon platform and build my data pipeline from scratch, so using Kinesis, Lambdas, Redshift, is there still a place for Elastic MapReduce? Or is it more like for legacy pipeline?
Well, it depends. I mean, and it also, as one of the previous speakers said, that it depends how much you want to get locked into the Amazon services as well. Because
so what would be the typical use case for using Hadoop and Elastic MapReduce?
well, I think it's if you have sort of custom data import processes that you want to run and you want to do a fair amount of computation on it. I don't know if we were setting it up today. I'm not sure whether we would sort of necessarily start from the same point because because the technology is changing all the time. But there's certainly if you want to do efficient large-scale data processing, then using an Elastic MapReduce cluster is a good way to do it. I'm just not sure whether some of the ones where we're doing actually a fairly straightforward import, that might be better done using some of the new services.
Have you tried Smack data architecture?
Sorry?
You have mentioned two data architectures, Kappa and Lambda, and there's one new data architecture called Smack. Have you tried that or?
No, so it's called Smack.
Spark, Mesos, Atlas,
Oh yeah. Yeah, I mean we don't use Mesos, as I say but there's a lot of different kind of configurations that you can do sort of around this. So this is just kind of like one example of how we did it in this case. But probably if we're using Mesos for other things, then we might consider doing that. Glue. I think we've been having a look into it. I haven't personally, but one of my colleagues has been experimenting with that. Yeah.
Does it work?
I think it's still you wouldn't build a production system on it just now, but it is quite nice in terms of how you can basically do kind of like a GUI, view of mapping the data, because I know when we're writing the data import processes, there can be a lot of repetitive bits where you're basically kind of going, okay, well, we're importing the data there, and then this is the Hive table, and then this is the definition of the Redshift table, so if you have like using that system, I think that it could be, as I say, it could be more efficient for writing and managing those processes. Okay. Any more? Okay. Well, thank you very much, everyone. And don't forget to rate the talk on the Codemotion app.